Hello, my name is Dr. Josu Etxaniz1. I come from the engineering faculty of the University of the Basque Country. In this presentation I am going to introduce you the proof of concept for impact and flaw detection in airborne structures we developed in our research group. All structures are subject to unwanted and uncontrolled bumps. For instance, when considering airborne vehicles, birds, hail and meteors are usual sources of collision. Depending on the location and energy of the impacts can weaken the structure critically. On the other hand, aging, scratching, corrosion and manufacturing flaws also weaken structures. Furthermore, the subsequent damage could not be visible, as it usually happens in composite-made structures. In addition, the cost of visual maintenance inspection, which is not negligible, sometimes could be just a waste of time and money. Literature reports many laboratory researches on impact and/or flaw detection in metal and composite specimens. They include instrumentation such as general-purpose oscilloscopes, which usually are limited in size, weight, and number of channels to take measurements. The size of equipment and accessibility for the structure integrity testing are not major issues when dealing with big and heavy structures as the civil ones. However, when the structures to monitor are lighter, such factors turn to be relevant. For instance, the integrity inspection on airborne vehicles requires reliable, low-volume, lightweight electronic equipment with high technical capability. This presentation focuses on the detection of impacts and flaws of structures in airborne vehicles with the same instrumentation. The setup of the test includes the structure under test, a set of transducers known as piezoelectric wafer active sensors or PWAS transducers, an electronic structural health monitoring ultrasound system known as SMUS, and the software to control the monitoring tool. Some piezoelectric transducers attached to the structure transform the electric signals into acoustic waves and vice versa. Acoustic waves propagate along the material and the waves change with any new imperfection inside the structure due to some damage. The tests are carried out on two types of materials: carbon fiber reinforced polymer or CFRP and aluminum. They show different properties for the propagation of ultrasound waves. The tests are carried out on two types of structures. Some of them were square plates, shown in the previous slide, and the other was a real-world leading edge, as we can see here. The leading edge was built by Arnova, which is a well-known metal and composite airborne structure provider. The first type of test is based on the impact detection system IDS included in SMUS. Any impact on the structure under test generates an acoustic wave that IDS must detect. The parameters of the waveform generated depend on the energy that the impact provides. As shown, two elements were necessary to simulate the energy of a real impact: a steel ball and a tube with a set of holes at different heights. If the mass and the height from which an object is thrown is known, the impact energy and object velocity can be calculated. We decided to use a ball due to its shape, because it has no edges and the same amount of pressure will be applied in every test, no matter if the object rotates. Finally, an SMUS is connected to the PWAS and to the laptop. Then, passive mode is selected in the control software interface to listen to the acoustic emission. Additionally, one of the channels of SMUS is also read by an oscilloscope to compare the data gathered by SMUS with the one measured by the oscilloscope. Thus, the precision and accuracy of the impact detection system can be analyzed. First of all, IDS was tested on two plates, one made of isotropic material and the other one made of anisotropic material, that is, aluminum and CFRP. Each plate has an array of PWAS located close to the edge of the plate. The goal is to compare the data read from the sensors when applying the same energy at the same distance from the sensors. Then, the tests on a real-world leading edge were carried out. Similarly, an array of PWAS was located on the part of the structure with the highest impact probability. The nearest location to the impact point, the less attenuated are the signals. It is shown in the next slide. As we did in the plates, an oscilloscope measured the signal provided by one of the transducers. A leading edge of any plane is a complex geometry structure. It is not thin, nor flat nor square, it is hard to model. Such kind of structures attenuate ultrasound waves much more than thin plates do. The red arrows in the picture point out the impact points of the test on the leading edge. The goal of the test on the leading edge is to determine the sensitivity of smooths to detect impacts, that is, the minimum impact energy necessary, the location of the PWAs, the effect of the curved shape of the structure, etc. As expected, after the impact, the leading edge is not apparently harmed. The second type of test requires not only the acquisition of signals as IDS does, but also the generation of ultrasound waves to apply them to the structure under test. SMOOS carries out such actions. Additionally, SMOOS preprocesses the amount of acquired data to simplify any further analysis and health diagnosis of the structure. Once SMOOS detects an impact, it is critical to know the degree of damage caused to the structure. The damage detection was performed following two types of tests in each structure. Round robin, one channel emits an ultrasound wave, see the yellow burst in the upper screen capture, and the echoes are acquired in all the channels of SMOOS, as for example the green signal. And beamforming, when the right delay is applied to each PWAS in the array, constructive interference happens in certain direction, and then an ultrasound beam is steered to that direction. Again, the echoes are acquired in all the channels of SMOOS. The damage detection tests were carried out daily during 2 months to analyze the performance of the guided waves through the structures. 2 stages were defined for these tests. The first one analyzed the effects of progressive damage, and the second stage analyzed the consequences of several types of sudden damage. Let's see the schedule for the first stage test. The initial state was set in the first days, when no harm was applied to the structure and the effects of temperature showed up. Then, during 40 days, the corrosion conditions were emulated. Saline water was added and the aluminum and composite structures were joined. Moreover, the room temperature was also measured every day. Next, the structures were separated. During a week, the room temperature was measured and the state of the structure was set as its initial new state. Eventually, a series of sudden damage were applied to the structures. Then, tests were carried out to measure the integrity of the structure. Several rest days were taken after each damage application. The set of sudden damage applied to the structures consisted of multiple impacts, hole scratching, and several diameter drilling. A steel ball thrown from a specific height was used to apply impacts to the structure. The corrosion emulation was achieved with hypertonic saline water with 2.2% salt concentration. The consequences of the corrosion in each structure can be seen in the pictures. There are several approaches to analyze the acquired signals. The first one consists of obtaining the DOH matrix, the degree of health matrix. The algorithm to calculate this matrix can be found in this reference. When the DOH matrix is green and the coefficients close to 1, the health and integrity of the structure is almost the same as the one taken as reference. The following video shows the evolution of the DOH matrix measured after each day of the stage 1 and after each sudden damage of the stage 2. As long as the health of the structure decreases, the coefficients of the matrix turn to be darker and closer to 0. As shown in the video, the test demonstrates that the health of the structure decreases with time. Note that the DOH matrix does not depend on the type of damage considered. It tries to determine the general health state of the structure, not the local damage. There is a second approach to the health state of the structure by calculating the average of the coefficients of the DOH matrix. As a result of the progressive and sudden damage applied to the structures, the average decreases with time, no matter the type of tests. See the figures. Note that temperature affects the measurements taken in the tests. The third approach consists of processing the acquired signals that show the highest variation in the DOH matrices. To finish the presentation, let's draw the most significant conclusions. The proof of concept for impact and flaw detection has been introduced. The methodology to perform a guided wave ultrasound test has been detailed. The test has been carried out on aluminium composite and a real-world leading edge. Round-robin and beamform techniques have been applied to the test. The effects of sudden and progressive damages on the health and integrity of the structures were analyzed. 3 approaches to analyze the data from the acquired signals have been introduced: the calculation of the DOH matrix, the average of the DOH matrix, and the comparison of acquired signals. The results show that the monitoring system SMUS not only detects impacts and flaws satisfactorily but also measures the damage as a decrease of the health of the structure under test. During the 2 months of tests, we performed more than 800 tests, which led to the acquisition of more than 100,000 signals. Nowadays, we are processing all these data. Thank you for your attention. Feel free to contact us for any questions you may have.